Today I'll be going over the Chapter 9 review for pre-calculus. The first section, numbers 1 through 7, is just matching with the formula bank on the right. So here are the answers for those. You can pull those from the notes. Otherwise, you will get these formulas on the test, so it's good to know which one goes to which scenario. I'm going to skip ahead to question 8 then. It says to expand the summation notation and find the sum. So basically what that's telling us to do is we're going to start at k equals 3 and just start plugging in numbers until we get up to 7. So plug in 3 first, so 3 squared minus 3 plus 4 squared minus 3 plus 5 squared minus 3 plus 6 squared minus 3 and plus 7 squared minus 3. Okay, I'm going to add all those together, and that should come out to be 120. We can use a calculator for that. Nice and easy. For question number 9 wants us to find the sum from 1 to 100 of this series right here. This is an arithmetic series. We can tell because it's got the arithmetic series formula in it, or the explicit rule for an arithmetic series in it, 4 plus 1 times n minus 1. And our formula for sum of an arithmetic series, so sum of the first 100 terms, is n over 2 times term 1 plus term 100. Alright, so we can fill in 100 for n. There's 100 terms. So 100 over 2 times the first term, which we know is right here, is 4. We can also get the first term by plugging 1 in for n. We get the last term, term 100, we plug 100 in for n, so we'll have n minus 1. 100 minus 1 is 99, and then plus 4, which is 103. Right, and we can do this calculation really fast. Should be 50 times 107, which is 5,350. Right. Number 10 is a geometric sequence or series. We can tell this as the explicit rule for a geometric series as our rule. It also has the convenient multiply right here. It helps you remember. It has the power, which tells you it's repeated multiplication. Both of those things will help you remember that that is a geometric series. So the sum for a geometric series 4 times 1 minus our ratio, which is 1/2, to the nth power, which is 6. And that 4 comes from the first term, which we know is right here again. That's our first term. And then we do 1 minus the ratio, 1/2, which if you put into a calculator, it comes out to be 7.875. When you're doing this, make sure you're careful about your parentheses. It helps remember your order operations and take it slow, step by step. Alright, and move on to question number 11. For question 11, it's this difference this time is this is an infinite geometric sequence. We're not able to sum an infinite arithmetic sequence, but we can do geometric ones. So sum of infinity here. Our formula is going to be term number 1, so 4 over 1 minus the ratio of 1/2, which is 4 divided by 1/2, which is the same as 8. So this infinite sum equals 8. So for questions 12 and 13, these are both arithmetic sequences slash series. What's going to be necessary for you to do if you don't want to write this all out in a calculator to continue the pattern between 19 and 79 is you will need to know how many terms there are. So you could do the first and last term, and you could use the formula for a arithmetic series. Otherwise, you can write them all out, count how many there are, find that there are 16. Alternatively, you could say set 79 equal to the explicit rule for a arithmetic series, which would be 4 plus the common difference in this one is 5, times n minus 1. Solve it for n, you would get 16 equals n. And then you can use the arithmetic sum formula, Sn, or S16 rather, since we know n is 16. S16 is 16 over 2 times the first term plus the last term, which is 79. Right? And if we calculate that out, that is equal to 664. Right? So I'll pause the video here. If you would like to try number 13 on your own, it's just like number 12. Go ahead. Alright, so the answer for number 13 is now on the screen. We'll go to question 14, which asks us to state whether each of these sequences is arithmetic, geometric, or neither. So remember that arithmetic sequences are addition and subtraction. Geometric sequences are multiply and divide, and then there's some that will be neither. So this first one, we are multiplying by 2 every time, so this is a geometric sequence. Part B, we add by 3, then 5, then 7, then that would be 6 actually. 6. Actually, these are not. Okay, so 4 and 5 go in between. This is actually plus 3, plus 4, plus 5, plus 6. We are not adding by the same thing every time. We are not multiplying by the same thing every time either, so this is a neither. Part C, we're adding by 2 every time, so this is an arithmetic. Part D, there's no consistent pattern here, so this is a neither as well. Part E is the Fibonacci sequence. 1, 1, 2, 3, 5, 8. It's just the sum of the first 2 numbers before it. This is actually you're not adding by the same thing every time, you're not multiplying by the same thing every time, so it's neither geometric nor arithmetic. And then F is, the pattern is dividing by 2 each time, so 2/3 divided by 2 is 1/3, divided by 2 is 1/6, and onwards, so this would be a geometric sequence. Right? So, moving on to question 15 on the next page. We want to state whether each infinite sequence converges or diverges. So what that means is, do the sequences get closer and closer to a specific number? So usually those numbers, that's going to occur when you have fractions going on. So in part A, if we keep adding new terms to our sequence, it's just going to go up to infinity forever because we're just going to keep putting bigger and bigger numbers in. So part A, this sequence diverges. For parts B, C, and D, these sequences will only converge if the degree of the top is equal to or less than the degree of the bottom. So the degree in B, so the degree of the top in B is the same as the degree of the bottom in B. So this would converge, and it would actually converge to 6 over 2, the leading coefficients, which is the number 3. For part C, the degree of the top is smaller than the degree of the bottom, so this would converge to 0. And for part D, the degree of the top is bigger than the degree of the bottom, so this one would diverge. The top would grow much faster than the bottom forever. For part E, these are fractions that you're adding 1 to the denominator every time, so over time the 1 on top is never going to change, which means that this number gets closer and closer to 0. Alright, for part F, this alternates between positives and negatives, which means it's going to alternate between a positive and negative number forever. The fractions themselves are getting closer and closer to 1. Basically what's going to happen at the end of the sequence is going to alternate between 1 and negative 1, so this one will diverge. For part G, this one, the fractions will get closer and closer to positive 1. The reason for that is the top and the bottom will always be separated by 1, so let's say the top was 1,000,000 and the bottom was 1,000,001. That extra 1 on the bottom is not going to make a lot of difference. It's going to be 0.9 for a long time and then like a 0.8 something. So basically it's going to be getting closer and closer to 1 as time goes on. Yeah. So that's question 15. Question 16 is a more real-world example, recursive rule writing. So for this savings plan, we need to write a recursive rule. So it's going to be Tn equals a bunch of stuff done to Tn minus 1, which is the term before it. If you remember from our exponential unit, how we add interest to an account is with something like this, 1 plus the rate of 3% divided by the number of times it's compounded per year, which is 4. So that happens every month, but we also have to take into account that every month we are adding $100 to it, so we have to plus 100 at the end of each compound as well. Yeah, so in order to write a recursive rule, we also need to know what the first term is. So the 0th month, your account balance is how much you start with, which is $500. And then we should also have a restriction on n because it can't just be anything. N is going to be greater than or equal to 1 for this one. So for part B, we want to know how much T24 is, which is a bit challenging to do with just a plain calculator, but you can just repeat the operation 24 times. I put my info into a spreadsheet, which told me that T24, which is 2 years worth of months, is going to be $3,093.85. Right? So that is chapter 9. And that is all.